Today, we're diving into a really fun, classic coding problem, finding the longest consecutive sequence in a totally jumbled up array. And it's one of my favorites because it shows you how just one tiny little tweak in your logic can take a solution from okay to absolutely brilliant. All right, so let's get right into it. Picture this. You're given an array of numbers, all out of order, like the one you see here. Your job is to find the longest chain of consecutive numbers hiding inside it. You can probably spot it, right? It's 1, 2, 3, 4. That's a chain of 4 numbers. So the question is, how do you get a computer to find that and find it fast? So just so we're all on the same page, what exactly is a consecutive sequence? It's just a set of numbers where each one is exactly one greater than the one before it. The real trick here is that they can be scattered all over the place in the original list. They don't have to be neighbors. And this is where the real puzzle comes in. We have to solve this in what's called ON time. Now, if you're not super familiar with that, all it really means is we can basically only look through our list a limited number of times. No nested loops, no complicated stuff that gets slower and slower as the list gets bigger. And this immediately throws a wrench in the most obvious plan, right? You might think, hey, let's just sort the array. But nope, sorting is usually too slow for this kind of strict requirement. We need a cleverer way in. So if we can't sort it, what's our secret weapon? Well, it's a fantastic little data structure called the hash set. Let's walk through our first attempt, our first blueprint, using this hash set. Okay, so why a hash set? What's its superpower? It's all about speed. Think of it like a magical dictionary. You can throw all your numbers into it, and then anytime you want to ask, hey, is the number 200 in here? It can answer you almost instantly. We're talking O of 1 or constant time. It doesn't matter if there are 10 numbers or 10 million. That instant lookup is exactly what we need to stay under that O of n time limit. All right, so here's our initial plan of attack. It's pretty straightforward. Step 1, we just dump every single number from our array into that hash set. Easy enough. Then we're going to loop through our original list, number by number. For each number, let's call it x, we'll start this little hunt. We'll look for x plus 1, then x plus 2, x plus 3, and so on, for as long as we keep finding them in our set. And as we find them, we'll yank them out of the set so we don't count them again later. All the while, we're just keeping a little scoreboard on the side to track the longest chain we've found so far. Okay, let's trace this thing with our example. First up is 100. We ask our hash set, hey, is 101 in there? Nope. Okay, so that's a sequence of just 1. Longest so far is 1. Next up, the number 4. Is 5 in the set? Nope. Another sequence of 1. Same deal for 200. We check for 201, it's not there. So far, kind of boring, right? Our longest sequence is still just 1. But now things get interesting. We hit the number 1. We ask the set, got a 2? And it says, yep, awesome. How about a 3? You bet. Okay, what about a 4? It's here too. Then we check for 5 and nope, our luck runs out. So we've just uncovered a sequence of 1, 2, 3, 4. That's a length of 4. We update our scoreboard. And remember, we pull 1, 2, 3, and 4 out of the set as we go. Okay, see what happens next. Our main loop keeps chugging along, and it gets to the number 3. But wait, we already found 3 as part of the sequence starting with 1, so we've already removed it from the hash set. So we do nothing. Then we get to 2, and it's the same story. It's already gone. So yeah, the algorithm works. We got the right answer, but you can feel it, can't you? We're spinning our wheels here, checking numbers we already know are part of another chain. And this right here leads to the big question. Why? Why are we doing all that extra work? Why would we even bother starting to count from 2 or 3 or 4? We know they can't possibly start a new, longer sequence because they're just middlemen. They're part of the chain that 1 kicked off. This is wasted effort, and getting rid of wasted effort is what optimization is all about. And that brings us to the aha moment, the big idea. What if? What if we only bothered to start counting when we found the real start of a sequence? If we could just find a simple way to identify only the numbers that kick off a new chain, we could skip all that other pointless work. So let's just put these two ideas side by side. Our first pass was kind of brute force, right? It tried to build a sequence starting from every single number. It wasted a ton of time on numbers that were stuck in the middle of a sequence. The optimized way, it's way more surgical. It only starts building when it knows for sure it's at a starting number, and it just skips everything else. Okay, so let's check out the final blueprint. This is where we introduce that one simple trick, that start of sequence check that changes the whole game. And here it is, the golden rule. It's so simple. For any number x that we're looking at, we just ask one question.
is x minus 1 also in our set? Because if it is, if its predecessor is there, then x cannot be the start of a sequence. It's just another link in the chain. So we just skip it. That's it. That's the whole trick.
So this one little check completely refines our algorithm. We still put everything in a hash set, we still loop through the numbers. But now, for each number x, we have this crucial gatekeeper check. Is x minus 1 in the set? If the answer is yes, we do absolutely nothing. We just move on. But if the answer is no, ding, 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 we found a sequence start. And only then do we bother to start counting upwards to see how long that chain is.
All right, let's run our example through this new, smarter machine. We get to 100. We ask, is 99 in the set? Nope. Okay, 100 is a starter. We count. It's a sequence of length 1. Next, we hit 4. We ask, is 3 in the set? Yes, it is. So we just skip 4. We don't do any counting at all. See? Then we get to 200. Is 199 in the set? Nope. So it's another starter, sequence of length 1. You can already see how much faster this is.
And here's the payoff. The loop gets to the number 1. We ask the question, is 0 in the set? It isn't. So our algorithm knows this is it. This is a real starting point. And now it starts counting. It finds 2, it finds 3, it finds 4, and bam, we found our longest sequence of length 4. And we only had to do the hard work once.
And just to finish it off, when our loop eventually gets to 3 and 2, what happens? Well, for 3, it checks for 2. Yep, it's in the set, skip. For 2, it checks for 1. Yep, in the set, skip. All that redundant work we saw in the first version, completely gone. We just breeze right past them.
And this chart really says it all, doesn't it? On the left, you've got our first approach, doing a bunch of work, checking all the numbers. And on the right, you've got our optimized version. Look how much less work it's doing. It only gets busy for the actual sequence starters. Now, technically, both algorithms are ON, but in the real world, the second one is just so much leaner and faster.
So when we zoom out, what's the big lesson here? It's really about thinking smarter, not harder. It's about that journey from just getting an answer to getting an elegant and efficient one. So here are the big things to tuck away in your programmer's tool belt. First, hash sets are your absolute best friend for any problem that needs fast lookups and has that OVAN constraint. Second, and this is a big one, your first working solution is almost never your best solution. Always poke at it and ask, can this be better? Third, optimization is almost always about one thing, killing redundant work. And finally, this idea of finding the true start of a problem, that's a super powerful pattern you can use all over the place to slash your computation time. And that really leaves us with one final thought to chew on. This pattern, this idea of identifying a valid starting point to avoid doing the same work over and over again, it's incredibly powerful. So my question to you is, where else can you apply this? In other coding problems, sure, but maybe even in how you approach problems in your daily life. Think about it.